as soon as we can so that those of you in the back will have a place to sit. My name is Jerry Spivey. I'm with Research Triangle Institute, and I want to welcome each of you here this morning. You'll notice from the program that has been put together for you here today that we have focused not only on deactivation but also catalyst regeneration. I think this is an area that's important for us to remember as we look at the working catalyst in industrial processes. And a number of our papers today will focus on that important aspect of catalysis. We will have, after each paper, during the period of questions, I'd like to ask each of you that has questions to step to a microphone and be sure to identify yourself and speak clearly so that others can understand the question and the response. Our first speaker today, our keynote lecture, is to be given by Professor Wojciechowski from Queen's University in Kingston, Ontario. Bo was born in Poland and educated at the University of Toronto and the University of Ottawa. And he's now a professor in the Department of Chemical Engineering at Queen's University. He will be speaking to us today about decay in cracking catalysts. Bo.
Thank you. Good morning. Good morning. I'd like to start off by posing for you 3 questions, which hopefully by the end of the talk I will have answered for you. One of the questions is, does the weight of coke on catalyst represent the extent of deactivation? And I think it's fair to say that in general the weight by itself does not do that. It would have to be that each increment of coke deposited on the catalyst has the same amount of poisoning capability for this to be true. And that, I think, is pretty well understood not to be the case. Second question is, does the time on stream relate to the extent of deactivation? And the answer here is clearly yes, as long as the reactants and the products have the same ability to poison the catalyst, because the catalyst spends all its time on stream in the presence of a mixture of reactants and products. Different proportions, and therefore if both are equally poisonous, the proportions don't matter. And that, in fact, you will find is often the case, because as you'll see as we go through the talk, it is the carbenium ions which arise from either reactants or products that are ultimately the agents of catalyst decay. And finally, there's a question, is there any relationship between the coke on the catalyst and catalyst decay? The previous question says, is catalyst decay a function of time on stream? Time does not decay the catalyst. Some physical agent, coke presumably, decays the catalyst. And we have here the answer to that. Yes, catalyst decay is caused by coke, but it is certain parts of the overall coke you observe that do the damage. Let me start off by showing you some data from some 20 years ago or so, when we looked at the relationship between...
to the top.
How's that? When we looked at the relationship between the amount of coke deposited and the time on stream. And the one thing you'll notice here is that the relationship is not linear. And more importantly, the relationship is dependent on the amount of catalyst that you're using, the cat to oil ratio of your experiment. So there is an additional factor in there in the accumulation of coke, which is how much catalyst is present. How much catalyst did you use to process a given amount of oil? If you look at it from another point of view, this is coke on catalyst against the fraction of the surface left unpoisoned. And as you see, that too depends on the cat to oil ratio. These are from about 20 years ago, and I would imagine most people have by now come to realize that the relationship between the amount of coke and the amount of decay is complicated. You can't just say one varies as the other as an exponential function, some such thing. More recently, we showed that as the coke on the catalyst ages, it changes in form. Here are 4 samples of coke on catalyst done by magic angle spinning NMR. After 15 seconds, if you look at it, the sample is fairly rich in aliphatic groups. As time on stream increases, the aliphatic component decreases and the aromatic component increases. I think, without this direct evidence, most people knew that coke hardens with time on stream. And when they said hardens, they really meant it gets more dehydrogenated, and this just puts it in terms of NMR modern techniques of tracking this behavior. One can take those 2 curves, take the area under the aliphatic and aromatic component peaks, plot them on a graph like this, and you get almost linear behavior. But I think if you try to go on from there and try to relate coke to decay and so on, you get stuck in a morass that leads nowhere. Let me therefore suggest that we realign our thinking a little bit and examine something that I'm going to show you now that is not yet in the literature, but in the next few months there will be a series of papers which tackles a topic that is fairly actively being discussed in the cracking community now, namely the role of chain mechanisms in catalytic cracking. Now, chain mechanisms were around many years ago in gas phase cracking when the Rice-Hertzfeld mechanisms were being developed. Then they disappeared for a number of years, and now it looks like they're going to reappear in a slightly different form in cat cracking, but the fundamentals remain the same. In order to have a chain mechanism take place, you must initiate the chain. The initiation reaction is usually the most demanding energetically. It is the slowest reaction in the whole process. And in this case, we propose that the chain is initiated by protolysis of, let's say, a paraffinic reactant. The protolysis can be in 2 distinct places here. We can protolyze off a hydrogen atom, making a hydrogen molecule, or we can break a carbon-carbon bond, making 2 smaller fragments. But one of these fragments is going to stay on the surface as a carbenium ion. The intermediate between the protolysis and the original reacting species is presumably a carbonium ion, a pentacoordinated transient state. So once we've done this initiating, we now have a carbenium ion on the surface. And as you can see, we can have different carbenium ions on the surface. In this case, I've shown 2, but there are other possibilities, as you can easily imagine. propose that each such carbenium ion can propagate the chain by reacting with the feed molecule, just like it was in the gas phase chain mechanisms. The propagating species is the carbenium ion on the surface. The reactant is the feed in the gas phase. So this is a radial mechanism kind of reaction. And in the propagating step, a number of possible moieties can be transferred from the gas phase molecule to the surface to the carbenium ion, liberating that part as a gas phase species, or leaving on the surface a larger species, as you see here. So here is one of the possible reactions that could occur in chain propagation. The most common one would be the transfer of a hydrogen atom from the feed to the surface species. If it happened to the surface species, as in this case, before rearrangement occurs, you would see nothing, except if you were doing isotopic mixing reactions. But if this species rearranges into an isomeric form before the hydrogen transfer is carried out, you will produce a paraffinic isomer of the feed. And this is the way that I say isomerization proceeds in these reactions. There's the chain propagation reaction. So we've had initiation, propagation. Each of them, you will see, has created carbenium ions of different kinds on the surface. If the surface carbenium ion is large enough, it can undergo good old beta cracking. Until not many years ago, beta cracking was the only thing we thought went on in the cracking process. Well, it does go on if the ion is large enough. And here is an example of it. This is a typical chain transfer reaction, according to the terminology used in chain mechanisms, in that we don't consume feed, because the previous two reactions, you remember, consumed feed. But we do change the nature of the propagating species from this to that. So it's chain transfer. We also produce a product in this case. And finally, for all stable chain mechanisms, we have to have a termination step, and the termination step must be equal in speed to the initiation step. The only reactions that don't obey this are explosions, where you have branching reactions, or runaway reactions of other sorts. But in normal reactions, and in this case, there will be a termination step, which consists of simply the desorption of a carbenium ion from the surface and the reforming of the original Bronsted site, the pristine Bronsted site. So we now have a mechanism which converts feed into products, and along the way there are two fundamental types of reactions: protolysis, which occurs on the pristine sites, and chain propagation, which could be the dominant process, because the chain length, which is the number of propagation steps that occur before a site is reconstituted into its pristine state, could be very large. There's no theoretical limit on how large it is. It all depends on the rates of various reactions there. So we could have 10 times as much material converted via the chain propagating step as via the initiating reaction. As an example, in gas phase kinetics, chain lengths of hundreds are not uncommon. And we have the termination step, and at each stage you will notice there was a variety of carbenium ions which can take part in the propagation reaction. That's complicated enough in terms of reactivity. You'll notice that each of these carbenium ions, because of its configuration and because of the size of the ion and so on, will have a different reactivity towards the feed molecule. That's not too difficult to imagine, right? But after we've looked at the major reactions in the system, we have to remember that as soon as some product accumulates in the stream passing by the catalyst, there will be olefins present, and olefins can add to carbenium ions the way we have shown here. And this constitutes a secondary reaction to begin with. It allows us to build larger carbenium ions on the surface. And this particular event represents a radial mechanism of dimerization. Another kind of dimerization that can occur is dimerization by the Hinshelwood mechanism, which takes place between adjacent carbenium ions on the surface. And here we have an example of such an event occurring. Now, obviously, this particular reaction will be reduced in velocity if there is a smaller density of sites on the surface, because this can only occur between adjacent carbenium ions. So if the sites are spread out, then adjacent ions are not going to be close enough to perform this act. But hypothetically it's possible, and what it does then is it introduces additional carbenium ion species that could exist on the surface. Okay? So what we're doing as we're going through this discussion here is we are seeing how a variety of carbenium ions might arise on the catalyst surface. These dimerizations that we just saw will lead to large ions, and large ions, which can be formed by surface dimerization or addition of olefins to carbenium ions, can undergo beta cracking very readily. The small ions don't seem to do that very easily, but the large ones do undergo beta cracking. They can also desorb, forming larger olefins, which are found in the products of such reactions. But there are two processes that these large ions can undergo that the small ones don't really suffer for. And I call them malignant reactions because they tend to produce species of much lower reactivity. The two are elimination, and I'll show you some examples, and cyclization. Cyclization may not be as malignant as elimination, but we can leave that for further discussion while we look at what I mean by elimination. So, elimination from that ion that we just formed by dimerization with an olefin or two carbenium ions adjacent on the surface, a species like that can throw off, eliminate a moiety, hydrogen gas, or methane, or something larger, although in general, smaller particles tend to be eliminated. Hydrogen and methane seem to be the preferred molecules formed by elimination. When an elimination occurs, we form a carbenium ion of an olefin. So it's an olefin ion. Species like this do not seem to desorb readily at all. If they did, you would get a diolefin product. Diolefins are very rare in the product. Not zero. Nothing is 100%. Nothing zero. but they are very rare. So once you form this kind of a species, it doesn't seem to want to unstick, to desorb. It can continue to eliminate hydrogen, for example, hardening in that sense as it goes along. It can be desorbed by a hydrogen transfer from the feed, in which case you would get the corresponding olefin coming up. Olefins, we do find, right? So this species sticks on the surface, can undergo a reaction with the feed molecule, but rather doesn't look too promising, and it certainly doesn't seem to desorb the olefin ion I'm talking about. After undergoing an elimination, as we just saw, the species can now eliminate, because in the previous case we eliminated two adjacent hydrogen atoms, and off they came as hydrogen, as a hydrogen molecule. But if the configuration is right, so you can eliminate hydrogen atoms from different positions in the chain, you could form a bond like this, which is the beginning of, which is cyclization, and subsequent desorption will give you an aromatic species. Now, this species will come off fairly readily from this. So once this cyclization of a small small molecule, relatively small, takes place, these things come off, and we do see aromatics as minor products, a great variety of them in the product stream. Minor, very small amounts, but they're there. So here is how we form aromatics by elimination, by sequential elimination of hydrogen. These things are, the literature already contains a number of examples of the composition, for instance, of the minor product stream. One of the papers we had reported a great number of minor products, but even for a molecule as simple as 2-methylpentane, you get this many primary products, and it's clear that each one of them comes from a different carbenium ion configuration, at least, right? I'm presenting this to show you two things: that there is, even for a simple molecule, a great many carbenium ions present, and that they are present in different amounts, and therefore will have different influences on the reaction, because each of these preceding carbenium ions that came off here as an olefin, for instance, was able to abstract a hydride from the feed and come off as a paraffin, right? It just had these alternative things it could do, and could have then contributed to the overall conversion process. So where are we? We've got a lot of different carbenium ions that exist due to the reactions inside the chain. There are additional carbenium ion species formed, such as the olefin ions, that are due to subsequent elimination reactions, and other ions due to dimerizations of various sorts. A dog's breakfast of ions, but all of them have a certain characteristic that we're interested in when we talk about catalyst decay. Namely, they have different reactivities towards chain propagation, right? And if that is so, then we can organize our thinking along these lines. Let's say that the activity of a catalyst can be decreased by two types of events. One is an event which I call sudden death. There's a perfectly good site, bang, it's gone, no more activity. Or there's a perfectly good site, a carbenium ion sits on it, and it's a little less active than the original site was. And then after a few more reactions, there's a different carbenium ion on it, and it's even less reactive, and so on. If we organize our thinking this way, we could put the activity levels in sequence, this being the most active and going down to less active sites. And at each reaction event, the activity can transition from here to the next lower level or to 2 levels down. You know, we don't really know what will happen in a given reaction, so we should allow all possible transitions to occur. There is some level below which the activity is such that that particular site will no longer convert reactant. Okay? Furthermore, we could also propose that from any of these activity levels, a lucky reaction can regenerate the original pristine site. We saw that in the case of, for instance, the olefin ion. If it manages to abstract a hydride from the feed, it will come off as an olefin, right? And we will be left with the pristine site, which is the original activity level way up here. Okay? This is the conceptual framework of what we're going to discuss. And now a little bit of mathematics, but not to the point of indigestion. We're going to look at a discrete model. We're going to say that the catalyst sites can be in these various states that we just saw, these levels, with state 0 being fully active. That might be the Bronsted site itself, and then decreasing in activity till we get to some point S equals M, which is completely inactive, S being the state it's in. On discrete occasions, when a reaction occurs, there is a possibility of change of activity of that state due to the fact that a different carbenium ion will arise on the surface, will be left there after the reaction, right? So there are discrete turnovers, if you will, in the activity of each site. Number 3 is that we let CK be the column vector of concentrations of these concentrations of sites in the different levels of activity. So there's so many of pristine sites and so many of activity level 1 and so on at some time k, okay? Okay, so there's also an initial condition of this vector, which may be that all sites have the same activity, or maybe there's a pre-existing distribution, but there is such a vector, right? And at each turnover, and we could synchronize them so that at each tick of the clock, the thing turns over simultaneously, we simply, to calculate the next concentration vector, we multiply it by the probability matrix, and we have this. If we do that, then the overall activity of the catalyst is the sum of the activity row vectors times the concentration vectors, which leads to this. The chairman is telling me I'm being too long here, so believe me, this is true. Because this is mathematics, this is nothing that I invented. That particular set of matrices also can be written in terms of eigenvalues, and here it is written in terms of eigenvalues, and then we can proceed to change the turnovers into a time function by taking a turnover number, which is the number of turnovers per unit time, and thereby change this k into a t. A few more transformations which are really algebra, and we get this function. This is the function which, for a discrete model, gives us the fate of activity on that catalyst. Since this is a sum of terms, sum of exponential terms, you will readily find that it is best simulated by the hyperbolic decay function that we use in the time on stream theory. I will now rush you through mind-boggling mathematics very quickly because of the time constraint. If we look at the same model as a continuous model, in other words, there is a continuum of activity levels, and it's not just 1, 2, and 3 different steps, then we write a function like this. I'm not going to excuse it right now for you. 2 things are important in this. There is a function which tells us how fast a given site decays at a given activity level and how much activity it represents. If we now substitute into this equation proposed activity behavior with level and decay behavior as exponential, we get an analytical solution that tells you that the hyperbolic function represents the decay of the catalyst, and we know what these constants mean. The same is true if you take hyperbolic terms. If sites can both decrease in activity and undergo sudden death, the same model will tell you that the behavior is perfectly well described by the time on stream decay function. If reactivation is possible, as I showed you on that drawing, from any state, the time on stream function will describe the loss of activity between the initial state and some final non-zero steady state. I think that is similar to what is observed in the case of ZSM, ZSM5, for example. And if on top of reactivation we superimpose sudden death events or some limits below which there is no reactivation possible, then we find a rapid decrease of activity initially and then a slow decrease towards zero activity. Both of them described by appropriate hyperbolic time on stream functions. Where does that leave us? It leaves us with the following, that I have shown you now the chemistry of what we believe goes on in catalytic cracking, how that chemistry relates to the accumulation of less and less active species, and how this accumulation, when written down mathematically, leads to a hyperbolic time on stream catalyst decay function. Thank you.
Thank you both. We have time for a few questions. We'll also bring in some chairs so that you will not have to stand through the next talk. We'll do that during the question period here. We have time for a question or two from the audience.
There's one back.
Rodney, would you step to the mic, please?
Have you considered the rate of coating by itself? If the rate of coating according to Voorhees is proportional to the inverse of the coat laid down, then we're saying that the more coat you put on, the lower the coat that is subsequently laid down. Now the rate of coating decreases as the coat goes up. Then couldn't you use for your argument also this particular point, since this would fit in with your malignant sites? In other words, as you grow these coat moieties or ions on the surface, as they go larger, the activity of these, not only for reaction, but also for coat itself.
Yeah, I would have to agree with that. Since coke formation, according to what I'm saying here, catalytic coke formation is really a malignant side reaction and therefore depends on reactivity available. It must decrease as the reactivity drops and as the coke accumulates. Thank you.
Thank you. We'll have to move on, but thank you very much.